So I want to do a little video just to summarize some of the information that's in the PowerPoint. It's, as always, there's a lot of info here. But we're doing 2 weeks of volcanoes. So this first week, we're kind of introducing you to the different types and why they look the way they do and some properties about them. We'll get into the hazards in the next module where we can focus on what types of hazards are associated with which. I mean, we mentioned them here, but this is kind of the basic, kind of the building block. So, if you look at a picture like this, which is Mount St. Helens before, and then you get a little, what happened after, you can see a dramatic difference there. So we want to figure out, what's happening here. Why are some volcanoes very eruptive, explosive, and other volcanoes not so much? You've either been to Hawaii, seen pictures of Hawaii. The eruptions there definitely aren't as explosive as, let's say, Mount St. Helens. And so there's things we can look at in the rocks that would tell us how a volcano might erupt and also what it might look like, the shape and stuff like that. So if we look at what controls the eruptions, there's a couple things that are doing that. So water in the magma definitely has an impact on how a volcano will erupt, its eruptive style. And so what happens is the water, like the rock itself at depth, is under pressure. And so it's in a molecular water form, a liquid. So as it moves to the surface and pressure is released, or there's a earthquake that fractures the rock, which releases some pressure, what we get is this quick change from a liquid to a gas. And so the water turns to steam. And of course, the gas takes up more space than the water does, so it expands. And as it expands, it works as a propellant, and it actually pushes the material out and can cause large eruptions. So the more pressure, more water in the magma, we can get larger types of eruptions. And so the other thing that's controlling the amount of water / gas in magma is really its composition. And so the viscosity, which is the strict definition, resistance to flow, is something that's going to impact the amount of gas that's in our magma or water. And so we have things like a mafic lava. So remember, and I'll talk about this in the next slide in just a second, but mafic is an igneous rock term that refers to the general composition. So these are rocks that have lots of iron, magnesium. The key is they have a low silica, SiO2, that's this right here. And having a low silica content allows it to be very fluid. Okay, and so it also has a higher melting temperature. The hotter it allows it to be fluid. So these types of rocks or magmas are not very explosive because the gases aren't trapped, or the water isn't trapped in there. It can escape fairly easily. It's really fluid. On the other end of the spectrum, we have felsic lavas or magmas. Remember, this felsic term has different elements in it and atoms, so lots of aluminum, potassiums, and things like that. Makes them light in color. And of course, they're much thicker because they have a lot more silica, SiO2. And that thick, gooey magma doesn't allow gas to escape. So as it tries to, or there's some expansion there, it can't get out and pressure builds. And this pressure over time can lead to a large eruption. So we want to look at fluids, gases, and waters in the magma, but also the viscosity. What's it made of? What is the rock made of, or the magma made of? Because if we can get the gases and stuff out easily, then we don't have a big eruption. So when we look at different volcanoes, the composition is going to dictate its erupting style, and it's also going to dictate what it looks like. If something is very fluid, when it comes out, it's going to flow for long distances, and it forms these broad, flat kind of volcanoes. The thicker it is, in general, the steeper the volcano is. And so we see that our felsic ones tend to be more explosive. But as a quick review, just the terms we use for igneous is mafic, intermediate, and felsic. They're very general terms that just describe the compositions of igneous rocks, but also of magmas and lavas. And so our mafic version here are the dark in color ones. So you might have heard the term basalt. This is what's coming out of Hawaii. It's very dark in color. It's very fluid. So low silica content means low viscosity, which means very fluid, runny. Felsic is the lighter colored igneous rocks when they cool and crystallize. A lot of silica makes it very thick and gooey, so a really high viscosity. And so as we look at our planet, and here's a little cross-section of a subduction zone, in general, if we were to look at some of the compositions of part of the Earth here, the continental crust is mostly felsic. And the oceanic crust, which is just this thin part on top, is mostly mafic. So we have mafic compositions here, felsic compositions here. Below the crust, which is a lithosphere, and this is the mantle, right? That's an ultramafic rock. It's even higher. It's way up here. But the idea is that when we melt the material in the mantle, we end up with mafic composition magmas. And so in this example here, where we're subducting, we're causing melting to happen in the mantle. Now, that material that's melting is mafic. As it rises to the surface, it can interact with different parts of the crust. It can interact with this mafic crust. So if I had, let's say, a hot spot right here, the hot spot would partially melt the mantle, which always gives me a mafic melt. That would interact with the mafic oceanic crust, and I would end up with a mafic magma or lava. But if we go over to the continental crust, you can see that even though we start with the same thing, mafic magmas, as it rises up, it now is meeting something new, some new ingredients, felsic stuff. And so lots of things can happen here. In general, the argument is that we have mafic because we partially melt the mantle. We start with mafic melt. As it rises up, it's going to interact with the felsic and give me something in the middle, an intermediate magma, which can erupt and form volcanoes. These are the most common types of volcanoes that we see at subduction zones because this is where we have continental crust. Right? So if we have a subduction zone between ocean, not so much. But ocean-continent, because I have that felsic material to add to the mafic, I can get a volcano that is intermediate in composition. This is almost all the volcanoes you think of. It's Mount Fuji, it's the Cascade Range, Mount Hood, Mount Washington, Mount St. Helens. These are all intermediate style volcanoes. Why? Because there is continental crust available, and there's a process to cause melting to occur in the mantle by this act of subduction. Now I can get felsic stuff here because it doesn't always mix very well. So there can be some felsic material that comes up to the surface because I have this felsic crust here. If we were to move inboard here and pretend that this is Yellowstone, there's a hot spot here. Well, my hot spot in the ocean crust had no new material. So mafic, mafic, mafic. I get mafic. That's Hawaii. Out here, I get a mafic initial melt, but as it comes up and interacts with the crust, it doesn't mix very well. And we get a pooling of this mafic magma at depth, which kind of heats up just the crust and causes mostly the felsic crust to melt. And then I end up with a second little chamber up here that's mostly felsic, and that can lead to these very thick magmas that can cause these super violent eruptions. And that is Yellowstone. Okay, so now that we have that, we look at where do we see volcanoes? Well, most of the big volcanoes that we kind of worry about or talk about, subduction zones. All along the west coast of South America, there's a subduction zone. Here is an ocean plate subducting under a continental plate. And so that causes melting in the mantle, which starts out mafic, but as it rises and intersects with this continental crust, it can give me lovely intermediate volcanoes. And that's what most we see here on the west coast, up here in the Cascade Range, out here in Hawaii, over here, over here. Most of these are intermediate style volcanoes. And it's because of the subduction process and the idea that as it rises up and impacts some continental crust, we can make an intermediate style magma, which can then lead to an intermediate type of volcano. So when you look through this slide presentation, I'm just going to introduce the different types of volcanoes and quickly just run through some of the properties of them. right? So when we talk about a shield volcano, so we're going to start at the most mafic. So these are the most fluid ones. And so what we see is a low viscosity because it's got a low silica content. There's not a lot of water and gas. Why? Because it escapes very easily. And so we typically don't get very violent eruptions. And so you can work your way through each of these volcano types and kind of just look at the general properties associated with them. And those are listed here on the side. So it's basically, what does it look like? What is the explosiveness? What is the composition? What is the gas content? Where do we find them, right? So you can kind of cruise through, and there's some lovely pictures here that kind of go with each. And so in Arizona, we do have a few. Arlington Mesa, Joe's Hill is a very small shield volcano. This is all dark black rock. It's across from Sunset Point if you're going up I-17 to Flagstaff. There's a really subdued hill here, but there's a little river that's cut through here and exposed the basalt here. Very dark rock, right? So you can take a look at that. Cinder cones. So now we're moving down the scale from mafic to intermediate and then to felsic. So we're still kind of in the mafic, but we've moved down just a little bit toward intermediate. So kind of in between, if you'd like, between mafic and intermediate. There's just a little more viscosity here. It's a little thicker, so there's a little more gas trapped. And so it has the ability to be a little more eruptive, but not super violent. And so what we get are these cones because it's ejecting material out in little fragments that shoot up in the air and then fall back down and kind of pile up into a little cone. And so these are still mafic because they're dark in color, but they're a little more toward the intermediate style. And then you can look through some of these. And then the most common type we see are these stratovolcanoes or composite. You can use either term. These are our intermediate ones. And so the intermediate volcanoes are a combination of explosive eruptions and thick lavas that erupt from the volcano and run down the sides. The term composite means that it's a composite of lava flows and then a blast that ejects material up in the air, which falls back down and coats the sides in what's called a pyroclastic flow or pyroclastic layer. And so you get this layered volcano, but they tend to be very steep because it's thicker magmas and lavas that erupt, so they can't flow very far. These aren't the most explosive because they're not the thickest magma. When we get to the felsic, those are the most violent, but these are the most common. And of course, there's a range in here. We're in the intermediate. You can have an eruption that's a little more to the mafic side, so not too violent. But if it gets a little more to the felsic side, it can be very violent. And so we want to say that these aren't the global killer ones that you might have seen a video on in Discovery Channel or something like that. But they're so common that there's more people that are around them. They're actually more of a hazard because they erupt more often. There's so many of them, and they can be very violent. So these are the ones that get most of the news because they're happening on a regular basis, and they have the potential to impact people and you potentially in your lifetime, whereas these other kind of super volcanoes really are something that happens every 100,000 years or more, so they're not as prevalent, and so maybe not something to worry about in your lifetime anyway. So you can look through the stratovolcanoes, different kind of references. There's a small feature called a lava dome that's used like kind of a secondary feature. You can kind of look through that, although very thick and gooey because it's very felsic, lots of silica. It's a second stage eruption with not a lot of gas in there. So without that gas and water in there, it really can't erupt because the pressure can't build, even though it's thick, right? But when we get to the kind of the last type, which is this caldera type volcanoes, this is the Yellowstone kind of thing. This is the idea that it is very thick and gooey, lots of silica, but there is just a ton of water and gas dissolved in there. So that when these things do erupt, they are massive. So you usually build a very large magma chamber, much larger than ones we would see in, let's say, Mount St. Helens or Mount Bachelor and the Cascades and things like that. So big that, and so thick, and the pressure just builds it. But it takes a long period of time, let's say hundreds of thousands of years, so it gets to the point where there is an earthquake as the magma is moving that ruptures the rock and allows the magma to escape, releases the pressure, and we have this massive explosion that drains almost the entire magma chamber, which can be, 50, 60 miles by 50, 60 miles, it's huge. And of course, this causes a collapse feature. As all that magma leaves the chamber, the rocks above actually fall into that empty space, and they tend to leave a caldera, which is the depression here. So a caldera can be used in two ways. One is a landform term. It's a depression caused by the collapse into a magma chamber. We're also going to use it as a type of volcanic eruptive style called a caldera type eruption. And this would be referring to these massive eruptions that, change the global climate potentially, right? So something like Yellowstone or things like that. These are the big crazy ones that probably you'll never see in your lifetime, but have the potential to do some damage globally. So that's kind of the big one, and then there's once more, and then some examples, just like all the others. So work your way through the slides and just kind of, familiarize yourself with the different types. The key here, the takeaway, of course, is that composition is really dictating what we see. We have big or small volcanoes, flat or steep volcanoes, right? Because of the way the lava flows when it makes it to the surface is related to its composition. It flows very fluidly, you get a different style volcano. If it doesn't flow very fluid, you get a steeper, thicker, potentially more hazardous volcano. Okay. That should do it for today.